Riedel. I'm the computing director for IceCube, so one of the major facilities out here. As you can see, this is the part of IceCube you can actually see. So this is just a general content warning. I know everybody has different experiences of things, so this is based on my observations and experience with Access or Exceed and its resource providers. So just as a sort of context, we heard a little bit about this earlier today, but basically Access is the allocation mechanism for NSF-funded HPC resources. So we had a list earlier today, but ultimately it is an allocation process, and this is by design, so it doesn't have any control over the CI resources. It's sort of a proxy in that sense. It replaced Exceed in 2022 and has a very smaller scope than Exceed had, and then Insight is sort of the DOE equivalent for those of us or view in the DOE land. And then the major facilities are usually $100 million plus NSF-funded research facilities. They're multi-user, multi-science facilities, so they have a very broad science reach and overall a very broad portfolio of science. So, so as we all know, the EMFs require a certain level of dedicated CI. So who provides that CI depends a little bit on the MF. There's a broad variety, but the normal model for Access doesn't really fit into that. So you can't really have shared resources necessarily, or this allocation process where you renew every year is not really a good fit. And of course, on the MF side, we have what I call the vertically integrated MFs. So this is the experiment to the final result, like CMS, Atlas, or the LHC experiments in IceCube and LIGO. And then you have resource providers or data providers. So this would be, for example, LSST and just so here are the examples. So LHC, yes, it is a very sort of vertically integrated. You go from experiment to final paper within a very fixed group of people. And the LHC experiment provide their own resources, do their own analysis, and basically present a paper at the end. While LSST, on the other hand, is sort of a science or discipline or community MF in some respects. It provides time for researchers, and they then go off and do something with that data. They analyze it, and it's quote unquote theirs in some respects. But LSST still needs to provide some data products. So, for example, calibrated data, but they don't really, once the data is taken, once it sort of has gone through a processing step or through their data pipeline, it's the researchers, and it's not necessarily in the auspices of the collaboration or the experiment itself. So quickly, what will we cover here and what the experiences of MFs with Access is, how Access and MFs could work together, and sort of what's missing right now in the Access portfolio from an MF or from a major facility perspective. So a big thing is the computing paradigms. The MFs are not sort of classical HPC. There is no mostly no tightly coupled workloads. You don't need to go more than one node. You have your ingeniously parallel workloads. And in sort of looking back in 2021 status, so AI or distributed AI training is really, a novelty at this point. And the EMFs are data intensive and mostly distributed in nature. So, it's organized chaos. So you're flying the plane and replacing engines sort of constantly. There's big data in and big data out. So it's not really, the classical HPC where you do a simulation, you have big data in and very little data out, very little data in. And the Access model is kind of oriented around data movement. So it orients around, you do your computation locally, you have your output, and then you move that data and you're kind of done. While the MS basically moves data back and forth constantly. So this and how does this look from the Access side? So this is this non-standard user conundrum for the Access side. So there's a large user base that's hidden from behind the EMF. So LHC, you have several thousand people or several researchers sitting behind sort of one account. The major facilities are sort of oddballs in the NSF portfolio. It's not your single PI, few PI project. It is, tens, hundreds of PIs, depending on which one you're talking about. And then, they usually need a lot of computing, and that means, you need to have access to more than one resource at a time, which needs to be very well motivated. There's a non-homogeneity also there, the workloads change constantly, or how they operate changes constantly. And then, of course, this brings in containers, and more containers. But on the access side, you usually also have sort of a non-homogeneity. You have some that do MFA, some that don't, or have sort of a workaround, different software stacks, the availability of resources, different policies. And that really makes it difficult to kind of say, oh, I'm going to run on Bridges 2 today, and I'm going to run on Expanse tomorrow. That doesn't quite work that way that easily. And the EMS has a large, complex software stack that needs to be moved around and centrally managed. And then the ultimate question is, it takes a lot of effort to integrate these resources into your pool. Is the effort actually worth it for what you get out? So sort of coming a little bit now to working together, there's lots of opportunities. Basically, access resource providers so across the board have all the CI that you have, all the resources that you need to build CI for a major facility. In the virtualization environment, you can go to Jetstream 2, CyVerse, Chameleon is sort of in brackets since they're not technically part of Access. You need storage, there's open storage network, there's storage at the various different sites. There's GPUs available, there's CPUs across all the boards. So everything basically to first order is there to basically build up your major facilities infrastructure, CI. But then there's a step back. So Access ultimately is a multi-user HPC facility, meaning they're focused on HPC workloads, HPC paradigms. There's sort of then there's this discontinuity between funding. It's a OAC size funds Access, and the major facility or the major facilities have their respective directorates. And then similarly, the Access resources are funded on a 5 to 10-year cycle, depending on the resource, while the major facilities are a multi-decade effort. So, the very large array is now in its 50th year, I think. And again, then also, besides sort of the major facilities, there's a lot of other users that have access. So there is sort of this question about, well, to me, as a resource, you only look at, you look as a user, you run your jobs and you're done. But you're technically, several hundred people. Similarly, the MFs have sort of this 24/7, 365 world where science operations happen all the time. So I know the Access resource providers have, I think, 95% uptime guarantees. And for example, IceCube's uptime is now not over 99% of the last 12 years. So it's a very different sort of, that last 4% is sort of where the issue, where the rubber hits the road. And equally also in the Access world, EMFs are just another NSFPI. They're not something special. So again, and this also becomes as a question of support. You go to a queue and you're in the queue, but are you special? Not really. You're just another user. So if your problem doesn't get resolved, it might be a few days to weeks. So working together, bringing it a little bit closer. So there's this low-hanging fruit of better homogeneity across the resource. That means why can't I do A, or why can't I do A, or rather, why can I use app-tainted resource A and not a resource B? Or why do I have to use this version and that version? Sort of, that just makes it more complicated. And of course, the MFA policies are not very well suited for remote submission, which is something that LHC and IceCube and LIGO do. But there's something where Access Path and the major facilities should collaborate on how to get that running. The other big sort of thing in the room is the AI resources. The major facilities can't afford, or I would rather say justify, spending a lot of money on AI resources. We simply put, a single A100 or H100 box is kind of sort of the maximum. But what if you need more? Just spending another 250, 500K is not really an option. for, a user or two. So that's where Access and its resources come in. And of course, hosting CI, ultimately, if the MF is hosted at a campus, there's always this friction about what are you doing, how are you hosting it at a campus, versus somebody who's hosting it with somebody who knows what they're doing, but also has experience of working with NSF and how that funding works on the hosting side. So, you don't have to worry about Internet 2 backbone or other things. You can just go to SDSC or NCSA or PSC and say, well, I want to put 10 racks of resources into your data center, and that would really be good for the MFs, just because it takes out a lot of headache when planning. Of course, there's economies of scale, but also requires some dedicated support. So coming sort of to the end here, sort of the missing pieces here are really archival. There's sort of the big example for me here is NERSC in the DOE, where you have one big tape archive that should serve the entire sort of smaller areas of the DOE. So and then you have, again, economies of scale that, if you have a tape archive that can host data from, let's say, LIGO, IceCube, and the other MFs, that's just cheaper at a single site rather than doing this at 10 or doing this at the various individual MFs. And there's also a sort of safety aspect here. When it's offsite, it's not necessarily, if something happens to the MF, nothing happens to the data. Of course, the easier support for distributed workloads. So this is, again, coming back to this remote submission issue. And then, IceCube, LHC, and LIGO as the big drivers here are kind of the beneficiaries. And of course, the common policies set across the access sites. And that's it from my side.
Okay, so wake you up, quick question. How many of you are running private LLMs that are trained on your documentation? How many of you want to run private LLMs that are trained on your documentation? Okay, I'm going to show you about what we're trying to do in this space. So I'm Tyson Swetnam. I'm Associate Research Professor at University of Arizona. I'm a co-principal investigator for this NSF project called CyVerse that's been around for 15 years. So the first problem is that you have to find the right platform. And if you've been paying attention for the last 6 months or 9 months, there's a lot of AI out there. And trying to decide which of these platforms is most appropriate for you to work with is almost impossible. So as always, you want to go and find the people that you know and you trust and listen to what they have to say. It's the only way to get there. The use case examples I'll talk about today, some chatbots that we're building with CyVerse, ways that we're deploying these LLMs inside of our workbench called the discovery environment, and then examples of using infrastructure as code, Terraform templates to launch these in a no-code environment. So the specific technology that I started using this fall is called RAG, or Retrieval Augmented Generation. This is the knowledge retrieval for documents. So if you come into the Chat GPT version Pro, you can build a retrieval bot now. You can feed it your PDFs or your PowerPoints, and then it will vectorize them and use them to retrieve information in its responses. Works pretty well. You can also go to their API interface in their platform, do the same thing, give it a prompt and give it your documents, and they'll give you results that are fairly accurate. The issue becomes an equity question when we build these chatbots for coursework. So let's say I want to build a tutor bot for a class. I'm now asking students that are already paying an exorbitant number of fees to the university to also get a $21 a month subscription to ChatGPT Plus. The alternative is that I shoulder the cost and I run it through the API. And when you run these responses, they're using lots of tokens. So an average response is going to cost you 3 to 6 cents per response. Start multiplying that by however many students you have in each section. They go crazy each night when they do their homework, and you're looking at maybe tens of thousands of dollars per course to try to run a chatbot. So we went back to the drawing board 2 weeks ago and started to design a new project. So this is what we came up with. We decided to go with the analogy of a ship. So we have our bridge as our control team. the propeller, the sails for running the LLMs, a rudder in the back end, a crow's nest for the UI, and then an anchor for the UX. So we locked everybody in a room for 3 days last week. We have about 25 or 30 software engineers. They were very disgruntled to be pulled out of their happy, warm homes and brought into actual campus to work together. But we had a good time. So they were able to put together an infrastructure in 3 days. We selected all open source tools. We're running it in Jetstream and in CyVerse. We built a Lang chain using the retrieval, found some open source chatbot UIs, and then we've got some questions that we're testing. So we decided to, or Nirov, the PI of CyVerse, decided to call it Project Chatter. So Chatter Vedi means a person who studied all the 4 Vedas and is therefore learned or smart. So we're hopefully going to land up with a smart chatbot at the end of this thing. This example of Ollama is running inside of one of our nodes at CyVerse. Ollama is an open source project. You can download open source LLMs. So you can pick your model, you can play with it and design it. So this is one example that we've got running on our workbench. It's just a Docker container and you can fire it up and bring your own models in there. Importantly, Ollama has a fast API backend. So we're able to run an API. We found another UI interface called Private GPT that you can select your own LLM for. We can feed it the documentation. This particular example is for a class that I designed about 15 years ago on the foundations of wildland fire. And so we're designing as our use case a chatbot for this wildland fire class. We ask it questions, we check to see if the answers are right. So far, it's okay. Our UI team is designing a user interface where the instructor can set up authentication so that you have to log in through your student account. They can then feed the documents. The student interface, they can then view their courses and they can select the course and then use this as a tutor. This user, Uba Buga, is perhaps well known to some of you in the room that are working with LLMs. They designed this text generation UI, and Edwin Skidmore, who's our lead for Jetstream 2, has a platform that we call Cacao, so cloud automation and continuous analysis orchestration. So this is a graphic user interface that sits on top of Terraform templates, and we're able to take the web generation UI, create a template for it, and a couple of clicks and 5 minutes later, you're running this UI on Jetstream 2, where again, you can download your own open source models and you can come in and do your model training. So this is an interface for folks that are interested in actually training their LLMs. So kind of getting close to the closing, there are these requirements. You've got to have serious hardware if you want to train these LLMs. If you just want to host a chatbot, you can run it on your laptop. But to make it in an infrastructure that can scale, so if we wanted to run this for a university, we're now thinking about running this on major facilities hardware like in Jetstream 2. It helps to have good storage and fast networking. We're focused mostly on these open source models right now. Mistral is dominating. It's up there above ChatGPT 3.5 now. It's just below ChatGPT 4. And then if you want to build your own models, you can run things in Jupyter Lab using conventional container environments. The last thing that we're stuck on is getting this thing ready for working with private data that are FERPA for students. So if we want to record information about these students and assess them, we have to get IRB. If you're working with health in a data enclave, you got to consider that or ITAR stuff. So last slide, think about cost containment. You can run this on-prem, so maybe you can run this in a cheaper way than you could on OpenAI. The security features of being able to run this in your own private infrastructure is pretty enticing for us. And then open source, I think, is the way to go forward and think about scalability. Thanks.
Hello, I'm Mike Zentner. I'm the PI for the SGX3 Center of Excellence for Science Gateways that you heard mentioned this morning. And that's what I want to talk to you about a little bit today. Is everybody here familiar with Science Gateways? No? Okay. Well, no, there's at least two. Traditionally, you might think about Science Gateways as there's a problem where people are behind this fence that they can't jump over the skills required to access HPC resources. And the idea of a Science Gateway was to open up a portal to those HPC resources through a simple website that would allow a lot more people to access scientific computing. Now, what I would like to do today to suggest that science gateways are really more about connections, platforms for making scientific connections. And certainly, yes, some of those connections are between software and supercomputers, but they're also between those things and massive audiences that didn't have anything to do with creating those things, but may want to use them for a variety of different purposes. They've also come to connect to expensive instruments that many people can't access on their own, but through a gateway they can. And as data have become a bigger part of what we do in computing, they become places where people access large sets of complex data that they might not otherwise be able to access or process. But one of the things, a little bit along the theme that Eva introduced this morning, is gateways have also grown to connect us to each other. They've become collaborative spaces where people share and work together on a variety of different things. So as you think about your work, what I would suggest is anytime you're thinking about an interactive web presence for the conduct of science or dissemination of results, that falls into the definition of a science gateway. And I would even change that a little bit to say, it's not just web, it's a cyber presence. There are many things we do with computing today that don't necessarily have a website in front of them. Now, science gateways are used for a variety of different sciences, some of which you see depicted here, but there's a lot more than that. They're used all over the place, really, and they have impact. So they have a scholarly impact. So the science gateway called CyVerse that computes phylogenetic trees has been cited today actually more than 10,000 times. That's a pretty big impact from a scholarly perspective. They have a collaborative impact. The NanoHub has tracked about 3,000 citations and looked at co-authorship networks that have formed amongst the people authoring those publications. And you can see from this chart how these collaborative groups of authors have come together over the years. And they have a financial impact. The Protein Data Bank, which hosts hundreds of thousands of protein structures that are used on a daily basis for new drug design, commissioned a study, and in that study, they estimated that it would cost $20 billion to reproduce the contents of that as it is today. So you might be thinking, science gateways, it's a website, how hard can it be? Right? We just hire programmers and we get a website. Well, on day one, that sounds pretty good when your award is fresh. But as you start to work through some of the decisions that you might make, if you make less than optimal decisions, you can actually do things that in the long term cost you a great deal of pain. And at the end of your project, maybe you've built up a lot of technical debt and there's not a lot you can do to overcome it by that point in time. So if you don't want to retrace the steps of others in a more painful way than maybe they've done it, that's where we come in. We're both a center of excellence as well as a software institute. The former is funded by NSF, the latter is funded by ourselves currently. And you can think about the Center of Excellence as focusing on forming a community as well as doing some consulting and advising services. I'll talk about a few of those activities. We have a workforce development component where we teach students and faculty how to incorporate science gateways into their curriculum. We do light touch consulting both on helping people think about sustainability plans, as well as technical architecture and technical advice. We do provide usability and user experience services. So if you're interested in having that kind of consultation, we can provide that. And we have two educational opportunities coming up. One is called Focus Week, and that'll be at TAC in Austin in April. And that's a week-long program to take people through the ideas about sustainability that they may need to apply to their projects. And we have an annual conference that this year will be in Bozeman in October. We'd be happy to see any of you there. Now, on the Software Institute side, if you need additional help beyond that, which we can provide with NSF funding for your projects, you can engage with us in more depth. And this can include helping you develop a full sustainability plan. It can include placing developers on your development team to solve specific types of problems. We can even completely outsource some software projects for you. In some cases, we provide professional operations services. So if you want to run a gateway, but you don't want sort of the IT hassles that come along with doing that, we provide that capability. And also professional graphic design to help things look really nice and professional. If you want to know more about this, you can access a thing called a storybook on our website at sciencegateways.org. And it'll go through many consultations that we've done. But one thing we did with each of our consultations was we asked people after they were finished, how long would it have taken them to do the same thing themselves? And they answered on the average about 6.8 times longer. So there is a return on investment in working with people that have done some of these things many times over. Now, gateways have always sort of treated computing as the center of what they do. And computing has been used to produce stuff, data sets, videos, images, all kinds of things. And we really have thought about the stuff that comes out of these things as its own sort of thing that goes off and lives somewhere else. But now as AI has become a much bigger part of what we do, I would say gateways are starting to have to treat that stuff as maybe the first class citizen, and computing as the appliance that allows you to operate and produce more stuff. With that in mind, one of the things we did as the Gateway Institute was we initiated and released a new project called One Science Place, which is a content-centric sort of gateway approach. There's still computing behind it, but when you go to One Science Place, what you'll see looks very much like content first, and you can operate on that content with computing sort of behind the scenes. So sort of a very different focus. And I think this becomes much more important, as I said, as we start to think about AI. So I talked about gateways being points of connection. And I think as AI enters the picture, they're also an important point of connection for us to AI, but in a different way than just connecting to data sets and connecting to computers. Now, what do I mean by that? So when you process a set of data or you run a simulation, you do it on your local resources, everything you've done remains local. And if you have hundreds and thousands of people around the world who do that same thing, all of that stuff remains local to wherever it is that they've done it. And it becomes very hard to collect it together to do something interesting with it. Now, if you do that same thing, but all those people are doing it under the umbrella of a science gateway, suddenly all that information about what they did and how they did it becomes captured in a common place that can be used for a lot of purposes that today we couldn't approach. And a lot of those purposes are automated. So from an AI perspective, we can, in some cases, we can automate the fairness of data. People don't have to take any extra step on their own to produce fair data. And this is actually happening today on one gateway that I know of very well. We can look at what's being simulated, and behind the scenes, we can robotically generate a lot more simulations and produce surrogate models that run much more quickly than their physics-based counterparts. And what that means is, once we have those models, we can move those models to where the data are, as opposed to always having to think, how do we move the data to where the computing is? Possibly big change. Those same fast models allow us to interact with the models much more quickly than we can with physics-based models. And what that means is we have the ability to essentially have a conversation with a model. And in conversations, we learn much more quickly than we do when we simulate things and go away for a day or a week and come back and forget the questions we even started with. And lastly, there's also the opportunity to intervene in how science is conducted. If you think about today, when you go out and use a consumer-based website, they're intervening in almost everything you do. Why can't we apply the same analytic techniques to do something other than sell us products? Why can't we apply those techniques to look at how the community is doing science and enrich that with the same kind of analysis that we would do with consumer analytics? So with that, I'll end. And if you're interested in learning more about any one of these things, I'm happy to talk to you about them later or answer questions about them now.